Welcome, everyone. Today, we are diving into MotherDuck, a revolutionary serverless DuckDB platform that operates across both the cloud and the client. We will be exploring the core concepts of hybrid query processing and what is known as the 1.5-tier data architecture. This presentation is based on the CIDR 2024 paper, along with official documentation, to provide a comprehensive look at how MotherDuck is redefining analytical workflows. Let's begin. The era of big data as we knew it is shifting toward a new paradigm: easy data. For years, the industry standard was the scale-out model. This approach relied on complex clusters of many interconnected machines, which inevitably introduced high latency and massive operational overhead. Maintaining these distributed systems became a significant burden for many organizations. Today, we are seeing the emergence of a new reality centered on the scale-up approach. Modern single-node systems are now efficient enough to handle the vast majority of enterprise workloads. This model offers instant elasticity and requires nearly zero management, allowing teams to focus on data insights rather than infrastructure maintenance. This transition is supported by a compelling reality. Over 95% of databases in existence are smaller than 1 terabyte, and more than 95% of actual queries involve less than 10 gigabytes of data. For these typical workloads, the overhead of a massive cluster is no longer necessary. By embracing single-node efficiency, we can achieve superior performance with significantly less complexity. The 1.5-tier architecture presented here represents a fundamental shift in how we approach data processing and application design. While traditional 3-tier architectures often create rigid boundaries between the client, application logic, and the database, this model enables logic to run on both the client and the cloud simultaneously. In the client layer, users interact through environments like a Python shell running DuckDB or a web browser utilizing DuckDB WASM. The integration of the MotherDuck extension is key, as it allows the client-side engine to communicate intelligently with the rest of the stack. The compute layer serves as the bridge, consisting of Duckling containers equipped with specialized storage extensions. These containers are designed to handle workloads that require cloud-scale resources, seamlessly offloading tasks from the client when necessary while maintaining a tight loop with the data. On the right, the storage layer utilizes cloud storage and differential DuckDB storage to provide a unified data source. Because computation is distributed across both the client and the compute layer, we can minimize data movement and maximize performance. This hybrid approach ensures that the responsiveness of local execution is paired with the power and persistence of the cloud. At the heart of our architecture is hybrid query processing, driven by a sophisticated remote local optimizer. This component is responsible for intelligently partitioning the query execution plan to maximize performance and efficiency. The core principle is to perform heavy computational tasks in the cloud while ensuring that local data remains on the client's machine. As illustrated in the query plan, the local client performs a sequential scan on its database, applying specific filters before the data is moved. Bridge operators, consisting of upload and download sources and sinks, manage the seamless transfer of this data between the local and remote environments. In the cloud, the Duckling engine handles intensive operations like reading massive Parquet files from S3, performing complex hash joins, and executing final aggregations. Once the heavy processing is complete, the results are efficiently downloaded back to the client. This hybrid model allows us to leverage massive cloud scalability while maintaining the integrity and locality of the user's data. Under the hood, the system is defined by 2 core pillars, the Duckling and our differential storage architecture. The Duckling represents the compute layer, where every user is assigned a dedicated serverless container. This environment utilizes morsel-driven scheduling to scale resources up or down dynamically and automatically hibernates during idle periods to ensure peak efficiency. On the storage side, we maintain a clean separation of compute and storage, leveraging an S3-backed infrastructure. Our differential storage system employs a mutation tree model, where writes are treated as separate differential files. This specific design is what enables advanced functionalities like zero-copy cloning and time travel, allowing users to branch their work or revert to previous states instantaneously without the need for redundant data duplication. Key enterprise use cases for this platform revolve around performance, efficiency, and security. First, for interactive data apps, we leverage WebAssembly to deliver sub-second dashboards. This provides users with near instantaneous feedback and a fluid interface experience. Second, our system excels at managing data pipelines by serving as an on-demand ETL compute engine. This approach streamlines data processing and reduces infrastructure costs by scaling resources precisely when needed. Third, we provide a solution for lightweight analytics. This serves as a nimble, simple alternative to massive traditional data warehouses, making it perfect for agile teams and rapid insights. Fourth, acting as a universal processor, we enable zero-copy SQL operations directly over S3 and Parquet formats. By querying data where it resides, we eliminate the latency and cost associated with unnecessary data migration. Finally, the platform functions as a secure data handler. It allows organizations to process sensitive information entirely in-boundary, ensuring that data remains within its secure environment while still enabling powerful computation and analysis. Authenticating to MotherDuck is a straightforward two-step process. First, you need to generate an authentication token within the user interface by navigating to the Settings menu and selecting the Create Token option. Once you have your token, the second step is to export it as an environment variable in your terminal. By setting the MotherDuck token variable, you can then seamlessly connect to your database using the DuckDB CLI with the MD:connection string. Following this method is a security best practice, as using immutables ensures that you do not hardcode sensitive credentials directly into your scripts or source code. Security controls in MotherDuck's SaaS mode provide a critical layer of protection for vendors embedding the service. By setting the MotherDuck_SaaS mode configuration to true, you effectively limit the platform's interaction with the host environment. This mode specifically blocks access to local files, local databases, and extensions to prevent unintended system-level operations. Simultaneously, it allows for secure communication with the MotherDuck cloud and the execution of SQL queries. This sandboxed approach is essential for maintaining a secure and controlled integration when embedding MotherDuck within your own applications. Database management within this ecosystem is defined by two primary modes, attach and share. Attach mode is designed for isolated connections, specifically utilizing the attach mode equals single parameter. This configuration ensures that a connection remains dedicated, providing an isolated environment that prevents external interference during critical operations. For team-oriented workflows, the collaboration feature allows for efficient sharing. Instead of duplicating entire storage volumes, teammates can view a consistent snapshot of the database. This is facilitated through a zero-copy URL, which enables multiple users, such as teammate 1, 2, and 3, to access the owner's snapshot simultaneously. This method maximizes storage efficiency and ensures that every member of the team is working with the same accurate dataset in real time. Integrations are about making your workflow as seamless as possible, which is why we support the languages and frameworks you already use. As shown here, connecting to MotherDuck in Python, Node.js, JDBC, or Go feels familiar and requires minimal setup. In Python, for example, you simply include your token in the configuration, while in Go, you use the standard SQL library. Across all these platforms, there are two mandatory requirements to keep in mind. You must use the MD prefix for all your connection strings, and you should always define a custom user agent. This ensures that your connections are correctly routed and that your application traffic is easily identifiable. Moving into the browser frontier, the WASM client allows you to run DuckDB directly within the user's web browser. By leveraging WebAssembly, we bring powerful analytical capabilities to the client side, reducing latency and offloading compute tasks. Integration is seamless. You can install the library using the npm command for the MotherDuck WASM client. As illustrated in the code snippet, establishing a connection is a matter of importing the connection class and initializing it with your MotherDuck token. This architecture creates a direct bridge between the local DuckDB instance running in the browser and the MotherDuck cloud, enabling high-performance data applications that function entirely within the web environment. Let's dive into the technical requirements for implementing WebAssembly with a focus on asynchronous processing and streaming. To leverage multi-threading through shared array buffer, the application environment must meet specific security requirements. This involves serving two critical headers, cross-origin opener policy set to same origin, and cross-origin embedder policy set to require corp. Regarding data retrieval, there are two distinct result modes to consider. The materialized mode is the standard approach, where the entire result set is loaded into memory simultaneously. In contrast, the streaming mode utilizes an async iterator to handle data in smaller batches or chunks. This streaming architecture is essential for managing large data sets efficiently, as it prevents memory exhaustion and enables real-time data processing. The performance argument for a hybrid approach is rooted in both speed and cost efficiency. Looking at these star schema benchmark results, we see a direct comparison between a local-only laptop configuration and MotherDuck's hybrid model. Across all 6 query types, the execution times for local-only processing, represented by the gray bars, are substantially higher than the hybrid results shown in green. This performance gap exists because scanning cloud storage directly via MotherDuck is significantly faster than the bottleneck created by pulling large datasets to a local environment. Beyond speed, this architecture also promotes sustainability. Utilizing local hardware reduces unnecessary cloud compute waste, while hybrid processing effectively offloads the cloud cluster to optimize overall resource consumption. MotherDuck offers a compelling value proposition centered on 4 key pillars. First, it prioritizes simplicity by utilizing standard SQL and eliminating the need for complex cluster management, which allows users to focus entirely on their data. Second, the platform delivers exceptional speed through its high-performance vectorized engine and a zero-latency local UI, ensuring a highly responsive experience. Third, MotherDuck provides hybrid power, enabling users to seamlessly join local files with cloud-based data for a unified analytical workflow. Finally, it facilitates effective collaboration by offering easy snapshot sharing, making it simple for teams to distribute insights and maintain synchronization across projects. Getting started with MotherDuck is a straightforward process that begins with signing up for an account at app.motherduck.com. Once your account is ready, install the DuckDB client by running pip install DuckDB in your terminal. After the installation is complete, launch the DuckDB CLI by entering the command DuckDB. To link your local session to the MotherDuck cloud service, execute the command .openmd. You will receive a success message confirming the connection. For detailed instructions and further assistance, please visit the official documentation at motherduck.com/docs.